Good day, everyone. I'm Dharni from SRM Madurai College for Engineering and Technology. In this video, we are going to discuss about combinational circuits. It's a heart of our digital systems. Yeah, while moving into a combinational circuits, first we are need to learn about the definition of the combinational circuits. It produces outputs that depends only on the present input values. The key properties of this is they do not store previous inputs, no memory elements or feedback loops are involved in it. The application we used in this combinational circuits are arithmetic unit, data routing, code conversion, signal selection. The topics today we are going to cover in this video is half adder, full adder, subtractor, demultiplexer and multiplexer. This is the features of combinational circuits. No memory or storage of previous input status are stored in a combinational circuit and output values depend upon the current input values. It is defined by the logical expression using Boolean algebra and fast operation as no clock signals are required. While moving into it, I have been given a logical gates for you to understand more about it. I have mentioned AND gate or NOT, NAND, NOR gate and XOR gate. Yeah, this is an example which we have mentioned in the first line. We are going to see in depth about it. While going into a half adder, the functions of this half adder adds two single bit binary numbers A and B. The output will be a sum. See, for example, here I have been mentioned A and B. In this sum, I have given A XOR of B produces 1 if input are different. The carry is A and B produces 1 if both inputs are 1. Okay. The implementation for this sum is XOR gate and for the carry is AND gate. The example which I would like to give you. See, while seeing this while saying this A and B, we are giving us an input and sum as a 0 and carry as a 1. The real-time example for this is used in a simple calculator for adding bits and binary counters and time circuits, where only 2 bits are involved. In the limitation for this is couldn't able to handle carry in the previous state. That's why we need to go for a full adder. Yeah, while moving into a full adder, I have been taken 3 bits A, B and C in. C in is nothing but carry in. For output, I have mentioned A, B and C in. Okay, for the sum. For carry out, I have been mentioned A and B plus B and C in plus A and C in. Okay, for this implementation, we have been mentioned 2 half adder plus XOR gates. Okay, for example, you can just kindly consider as A is equal to 1, B is equal to 1 and C in is equal to 1. Then the output would be a sum is equal to 1 and carry out will be a 1. For the real-time example, it is used in digital ALUs inside microprocessor and embedded system for multi-bit addition. Okay. For example, in computer for arithmetic operations also we have been used. Full adder or cascaded to form ripple carry adder for adding large binary numbers. Yeah, now we are going to see about a subtractor. In the subtractor, functions brings about a binary bit B from a bit A, that is A minus B. The output would be a difference and borrow. For the difference, I have mentioned XOR and for borrow, I have mentioned AND gate. For example, you can just kindly consider A is equal to 0 and B is equal to 1. Then the output will be getting as a difference is equal to 1 and borrow is equal to 1. The real-time example for this is used in digital clocks to calculate time difference and digital counter and digital comparators and subtracting operation inside the ALU processor. Okay, subtractor are combined in arithmetic units for both addition and subtraction for a complement logics. Yeah, now it's time to see about a multiplexer. Selects one input from many input based on the selection lines. For example, 4 is to 1. Here we have 4 inputs, 2 selection lines and 1 output. For this implementation, we need AND or NOT gates forms the selective logic. For example, if S1 and S0 is equal to 10, then the input I2 is routed to the output. The real-time example will just go on. It is used in communication system to send one of a many signals over a signal line. For example, voice data switching, like that. In CPU registers, selecting data from various registers to the ALU. For control units in embedded system, selecting sensor data. For extra points, we can just have it is reduces hardware by sharing one data path for many signals. Yeah, now we are going to see about an opposite of multiplexer that's named as a demultiplexer. Demultiplexer defines a routes a single input to one of the several output based on the selective lines. For example, here I have been mentioned 1:4 demultiplexer. We are going to get one input, two selection lines and four outputs. Okay. In the implementation process, we need AND and NOT gate to determine the output activation. For example, there we have been taken S1 and S0 is equal to 10. Here we are going to take S1 S0 is equal to 1. Input is routed to the output Y1. The real-time example we are going to mention here is for memory system, we addresses decoder to select specific memory location. For digital displays, we are going to direct the data to specific display segments. For communication system, we are going to use this as a serial to parallel data conservation. For see, often paired with MUX for complete communication system, and MUX are transmitted to DMUX as a receiver. See, for example, in the communication system, MUX actually act as a transmitter and DMUX actually act as a receiver. In this slide, we are going to see about the application of combinational circuits. Before moving into it, we are supposed to think about how the combinational circuits work into it. It produces output that depends only on the present input values, as we have discussed this in a previous slide. And this is a heart of a digital system. See, in this day-to-day life, we can't able to sustain without a digital system. So we have to think about it. And for this application, I have given arithmetic and logic units, data processing units, and code converter, encoders and decoders, digital system and communication device. While seeing this diagrammatic representation, you can easily understand how the combinational logic circuits is worked. See, it is segregated into three. One is arithmetic and logic circuits, and one is data transmitter circuits and code converters. See, while moving into arithmetic and logic circuits, we have adder, subtractor and comparators. While going into a data transmitter circuits, we have MUX, DMUX, encoder and decoders. MUX is nothing but a multiplexer and demultiplexer. Yeah, for code converter, we have binary and binary coded, decimal and 7 segments. See, here we'll be having all but code converters, so that we can able to easily understand how the combination logic circuit is segregated. Then actually final message I have to give an overview of it. The combination circuits forms the backbone of digital processing. They handle data efficiently without memory, performing tasks in real time. So I hope this is more useful and more understandable for you to know how the combination circuits is works and how the element and data code converter have been segregated. Thank you for your valuable time. Yeah, thank you so much.